Good afternoon, everyone. My name is Nicholas Hagen. I am a senior software engineer at Netflix. I'm here today to talk about managing contextual data across gRPC microsystems. Before I jump in, a little context on myself, pun intended. Fun fact, this is actually my first public speaking appearance, so bear with me today if you will. I'm not used to doing this. As mentioned, I work at Netflix, specifically within the Java platform team. So our team is responsible for building consistent platforms to improve developer productivity. This includes managing RPCs across our large distributed microservice architecture. gRPC is our most widely used RPC framework, so we're obviously heavily invested in gRPC technologies, which is why we're here. We run thousands of gRPC servers across our ecosystem, and we service millions of requests per second. Today we're going to talk about how we manage context at Netflix. This includes, first and foremost, what I mean by contextual data, what is it and how is it used. We'll discuss some of the lessons learned from our prior architecture. This is actually our second version of this architecture, and then get into how we manage and define that actual data. We'll discuss some of the difficulties in propagating that data, and ultimately how we transport that data across the ecosystem. We'll conclude with a brief overview of how we ensure success through observability. So let's start with a quick overview of what contextual data is, what I mean by that. So basically, it's any general purpose metadata, and it's often structured data models that correlate to specific feature requirements. This data is secondary and unrelated to the actual requests themselves, and it generally represents some sort of cross-cutting concern. This provides additional service capabilities, helping to enhance services. These features are often bundled within our frameworks themselves and flow independently of the actual request. So let's look at some examples. First, failure testing is used to inject errors into services. This allows us to change the outcome in order to produce and validate failure scenarios. How many have ever heard of Netflix's chaos engineering culture? Okay, quite a few of you actually. Good, nice. So we leverage context propagation here in order to target those specific services and then inject failures in order to validate certain behaviors. Second, services may want to do some level of custom routing based on that specific context. This may include things like A/B testing, canary testing, etc. For example, we might want to inject the specific clusters that we want to target, or use device identity in order to figure out which, from that context, to route to different shards. So this allows services to make routing decisions based on that context. Finally, a big use case for us at Netflix is enhanced resiliency features. This allows services to inject and maintain contextual state across the entire call graph. This includes things such as request prioritization and load shedding. Did any of you go to Benjamin Fedorka's presentation last hour on load shedding? A couple of you did? Okay, nice. So some of you all have some of that context here and feel more familiar. So load shedding is really managed by this idea of context propagation. So we can manage that priority at the edge and then use that priority on overloaded services to manage that load shedding behavior. This helps us to reduce load by ensuring that critical requests succeed while failing the less critical request. We also provide context back upstream for situations like back pressure relief. This allows services to back off calling specific instances that are overloaded or to even call alternative services. We identify this data as bidirectional as it flows not just downstream, but also flows back upstream. Another example is retry budgets. This can ensure that we maintain a fixed set of retries, not just across a specific service, but across the larger ecosystem. This helps us to reduce potential retry storms by tracking the number of retries across the entire call graph during that request. Before we get into some designs that we used, let's talk about some of the lessons learned from our prior architecture that really help to inform us of our decisions going forward. First thing we notice that is ownership is really critical to understanding data usage. Knowing where and what data is published and consumed and by who owns it helps us to simplify those support models. It also helps us to determine where that data originates during request and during support issues and which teams to ultimately notify. Second, features over time can greatly increase payload sizes. This can lead to failures due to exceeding the max header limits on certain requests. So tracking those sizes and defining explicit limits within the data models really helps to control impact. Next, new languages are constantly being adopted, leading to large polyglot ecosystems. Within Netflix, we have cases of Java, we have Node, we have Python, we have some Go, and various other languages. We have quite a few languages. This requires strict contracts on transport and serialization, and it's difficult to change after the fact. So you really want to require upfront thinking around that standardization and also ensure we use language agnostic capabilities to ensure we can align across all these languages. Similar, managing multiple frameworks across the different protocols is also difficult to support. So we leverage within Netflix what we call the paved path. This is our specific set of highly opinionated frameworks. So it limits our maintainability by only focusing on a limited set of implementations. So instead of supporting Apache or all different RPC clients, we only support a handful of them, so we can really ensure we kind of support that. However, services that don't adhere to that paved path are difficult to then integrate. This can cause the propagation to be lost because they don't have propagation enabled, and then we lose that context across the entire call chain. So managing the context propagation across services and even across threads within a service is also difficult to manage. But this is required to ensure that that data flows freely and consistently across the entire call graph, which we'll get back to in a second. But let's talk first about managing data. So the data is the most critical aspect of maintaining the context. We ensure data owners are first-class citizens in this architecture. Data owners own their specific data for the features that they are building and provides them greater control and flexibility when designing those features. We provide this capability by leveraging protobuf. As mentioned, Netflix has a very large polyglot ecosystem. So protobuf helps us to define those language-agnostic data models to ensure that broad level of support. Plus, protobuf is already heavily aligned with gRPC, so it naturally complements the ecosystem. Protobuf simplifies our code generation across these languages, and we can even enhance this capability by leveraging custom extensions. This helps us to generate better data abstractions of the data and use things such as observability by including that in the generated code. Further, protobuf provides us both backwards and forwards compatibility, helping to ensure our data evolution and migrations over time are easier to manage. Finally, we centralize all these data models into a common registry in order to simplify consistency, code generation, and dependency management. This also allows service owners to easily discover and adopt these features directly into their services. So let's look at an example. So first, as mentioned, we leverage protobuf to define the actual underlying models. In this case, we're specifically using v3. We then leverage code generation using protobuf plugins. So we define those language bindings for each of our supported languages within the model. Then we have our actual data that is exposed by this context. This is the structured data within the context that correlates to a specific feature requirement. In this example, it's a single field, but in other models, might have multiple fields or even multiple complex types. Finally, we provide a set of custom extensions. This provides context-specific information that's used within the framework. This includes both ownership information as well as contextual identity. Defining the ownership within the model aligns us on a single source of truth, allowing us to track that ownership much easier over time. We also leverage this information within the framework for observability purposes. We then define identity information on how the data is used and what features it might support. This is managed by a contextual key that maps the context to the features that it supports. For example, we might specify that a key is downstream only or also bidirectional flowing back upstream. Let's switch our focus to talk about context propagation. So what is context propagation? What do I mean by that? So at a high level, it's managing the contextual data within a service using specific life cycles, such as a unary request and response. Although we can also target other types of requests, such as bidirectional, streaming, etc. This ensures that data flows across the confines of a specific request. The context is managed centrally within the service and provides access to the underlying data on a per request or per lifecycle basis. This is also used to propagate that data across threads. gRPC by nature is heavily multi-threaded, especially within Java. So propagation helps to ensure that we have that same data access to that context across those threads as that request is moving across. This is similar in essence to the gRPC context some might be familiar with. However, we abstract that out in order to support other protocols and other frameworks, such as REST and GraphQL. This allows us to support the entire call chain across all of our different frameworks that we use. Ultimately, we have client and server-side RPC frameworks that transport that context across all the services in the ecosystem, ensuring that we propagate that context everywhere per request. So let's look at an example. So this is a real-life call graph at Netflix. This demonstrates our complexity and the widespread call chain that exists. Obviously, you can't read anything here because it's very zoomed out, but that's the idea of all these different services in these green boxes. So these are often across multiple protocols, multiple frameworks, and even multiple languages. So we have lots of stuff going on here. So let's go back to our use case again, talking about load shedding. So imagine we have a service towards the bottom of this call graph that's constantly being overloaded, and we want to manage load shedding based on request priority. However, the problem here is that request priority is really calculated by our edge router at the start of this call chain. So how do we ensure that request priority can flow down to that overloaded service? The naive solution could be that we simply add request priority to every single service, to every single request, and every single data model. Obviously, that'd be highly inefficient, require multiple touch points, and priority is really ancillary to the actual request itself, so it's not worthwhile to kind of mix those concepts. Instead, by leveraging context propagation, we allow that priority to be published across the entire chain. This allows any service to then consume and manage those features very generically. For example, we could easily identify the original request priority on an overload service at any point in this call chain in order to shed that load or manage other features. Often these features are then bundled with our paved path offerings, making service onboarding much easier. So how do we actually propagate and transport this data across all these services? As mentioned, we highly leverage our paved path and our customized IPC frameworks. This ensures that all services are consistently using the same set of RPC clients and servers and the features that they support. Within gRPC, this is managed by using custom client-side and server-side interceptors. These are included by default in our customized IPC frameworks that our customers end up using. These interceptors are then responsible for serializing and transporting that context across each request. For serialization, we use protobuf to serialize those data models into binary format, and then that binary format is then transported using request headers and response trailers. This ensures highly efficient payloads that are language agnostic and framework agnostic. So let's look at a simple workflow for a unary request. First, custom frameworks may publish context for a downstream service. For example, the request priority may be set in the active context at this point. Services may then send gRPC requests to other downstream services. At this point, our custom client-side interceptor handles that request. It serializes the current context from the protobuf models into that binary format, and then attaches that data as metadata headers onto the request. gRPC then sends that message and those headers onto the server. When the request comes in on a gRPC service, our custom server-side interceptor then handles that incoming request. It first reads that contextual data from those specific headers per our agreed-upon transport contracts, and we deserialize that data back into protobuf models and propagate that into a new context. This ultimately starts a new lifecycle for that context and associates it with that specific request. This allows gRPC to then call the underlying service method for that stub. At this point, custom frameworks may leverage that context to manage their features and perform decisions around this data. For example, at this point, frameworks could read that current request priority from that context to determine if load should be set or not. Services may even update the context, such as changing the request priority to become a more critical priority for other requests back upstream. So once that service finishes its request, the response is sent back to the original client. First, the server interceptor has to handle that response to send back any contextual updates back upstream. However, since our client already knows the original context and the original data models, we only need to send back the actual updates that occurred. So we automatically detect and capture those changes as field mask updates. This creates smaller, more efficient headers that flow back upstream. These field masks are then serialized into that binary format and attached now as response trailers. That response is received back by the client, allowing that client interceptor to handle the response message and read those response trailers. The client is able to deserialize that back into protobuf field masks, and then those masks are merged back as updates into the original contextual data. This allows the original caller or frameworks to then consume those updates or further propagate that down to subsequent RPC calls. This whole process is repeated across all of our services, allowing that data to freely flow consistently across the entire ecosystem. So with all this data flowing, how do we observe the data and ensure success? Ultimately, we do this with tracing and metrics. First, metrics helps to inform us what data is propagating and across which request. This includes which keys and data models are being used and by what services. This helps us with managing data migrations by easily identifying publishers and consumers of that data. We also capture data serialization and header sizes over time. We create alerts around this in order to consistently stay within our expected limits and avoid header limit failures. Finally, we monitor how data is transported across the entire ecosystem. This allows us to identify when services are potentially not propagating data. Loss of propagation by far is our biggest common issue that we face, where we lose the context on layer services. We also rely on tracing to help pinpoint exactly where that context is potentially lost. So our IBC frameworks add span attributes to those requests that track what keys are being propagated at both the client level and the server level. So we can see when the client sends it and when the server actually receives it. So ultimately, we generate dashboards and alerts and tools around all this data, ensuring we can constantly monitor the success of the system. So let's quickly review. So first, data owners create and publish their data models in protobuf, and they own their underlying data. Second, data owners create cross-cutting frameworks, publishing and consuming that underlying context. Our paved path adherence ensures that services operate consistently and automatically adopting those features. Third, gRPC interceptors transport the contextual data throughout the entire ecosystem. This occurs by serializing those protobuf models into binary format and attaching it as both request headers and then response trailers on the way back. This ensures data flows throughout the entire request, ultimately providing that rich business value throughout. This includes features such as enhanced resiliency, custom request routing, or even failure injection testing. And with that, I'll take any questions. Thank you. Like a question over there to the right, or your left. There we go.
Yeah, so a question I have is you talk a lot about losing context. How do you handle that? Because I can see how you have the interceptor sitting on both sides. They're handling processing of that metadata for that context. But when you're actually like writing business logic inside your service, how do you prevent the engineer or the developer from not passing that forward? Does the framework have guardrails, or what's actually happening there?
So really the two biggest issues for us with content propagation, one is threading, and then the other is things that don't abide by our paved path. So with threading, especially in Java, if you don't use the right executors, then a lot of times that we maintain basically within thread locals. If you're familiar with Java, we use thread locals to kind of manage that context across requests and associate it. But if you don't use the proper framework pieces, then you can kind of lose that context and not propagate into those threads, and then that doesn't get sent down. So our RPC frameworks know how to transport the data generically, and so the business users don't ever have to worry about doing anything with the context. They just use our APIs to say, hey, add this data model to your underlying request, and then the framework does everything else for you. So if you use our paved path, everything just kind of naturally works, everything automatically works, but if you don't, then that's where you get into troubles. And usually, business owners don't care at that point. It's usually when you're trying to consume something, you're like, oh, why don't I have a context? So like, why am I not actually using this data? And it's because something happens in that propagation being lost. So we have traces that we actually have a tool around tracing, allows us to kind of see where those keys propagated in order to see like, oh, this service here sent it, but then this one did not actually receive it. And so we can go back to that search and like, hey, what are you doing in your frame or in your code differently that's not using our paved path in order to kind of identify and then fix those issues. But yeah, they're extremely hard to track down.
So essentially you're saying by using thread local storage, you don't have to have the developer who's implementing the business logic think about it. It's just automatically being picked up by the interceptors?
Yep.
Okay.
Exactly.
So my question is, how do you do context propagation with gRPC streaming per message basic?
So we actually, right now, on Netflix at least, we don't really do a lot of streaming, but we're actually looking at it because we have some new products coming up. So our idea there is, because you really can't do response trailers in streaming because your trailer is attached at the very end. It's at the very front of the request header. So we're actually looking at having defined payloads for those messages that our framework would then kind of inject into that payload. So for each message that gets sent out, we'll have like a wrapper payload that then we'll attach the request to, and then when it comes back, assuming it's bidirectional, we can attach that response on the way back. If it's not bidirectional, then yeah, you really can't do the ability to kind of manage those upstream data updates.
Just following on that, for other languages where you don't have thread local, like in Python or PHP and others, how do you do this?
There's other languages outside of Java? Just kidding. I'm not a Java person, so. But within Node at least, I mean, Node doesn't really have threads at all. So I think everything's kind of assumed on the same request boundary, so you kind of just attach it that way. I don't know how our Node implementation actually does things. Python, I have extremely very little experience with. But as long as you like the gRPC context that's in most of gRPC's frameworks, it kind of allowed to tie to those requests. As long as you kind of hook into that aspect for gRPC, you can kind of ride that context and use that. If you're doing things like REST or GraphQL, it's kind of, you have to implement it in a certain way per framework and per language, which is why we really want to have this idea of paved path that we don't want to support OKHTTP and regular HTTP clients and RHTTP clients. We want to really say, well, we only want to support a finite set of clients, so we can add the implementation to each one of them instead of having to support everything under the sun, because that just won't scale.
How do you resolve conflicts in the metadata if like there's fan out, for example?
So when you're going downstream, you don't have to care because the data is only flowing that direction. When you're going back upstream, you have to merge those back in. It definitely gets more problematic. We're still playing with a lot of that to try to figure out, especially when you have a very heavy parallelized request, that you have a lot of them coming out at the same time. Like GraphQL is a big concern with this, where it makes 10 calls all at once, they all come back, and then how do you merge those updates back in? So we try to limit what upstream data is in order to limit how much we have to actually merge back in, because the more complex you get, the harder that conflict resolution is. So if you limit your fields coming back, it makes less of a impact of it. But we're still looking into how we manage that. Right now, it's very simple of just kind of whoever was last one in wins, and then you kind of propagate that back down. But we're looking at things too, like how far should data flow back upstream? Like, do you want the data flowing all the way back up to the very top, or do you want to limit, say, well, I only want the data flowing up one level or two levels? So there's lots of areas we can go around this, and we're still kind of early in the stages of how far and how much resolution we want to do around that data. So we're still learning a lot there.
Thank you. I have a couple of questions. First, do you have use case where you need to propagate context over pops up versus real-time API?
We don't yet, but as we get into more of the streaming use cases that we're looking at, we'll probably do something similar where we kind of, instead of trying to attach it to the headers, we'll probably use some sort of wrapper message in order to then add that wrapper to our message being published, and then you subscribe coming back. But we haven't really looked into it too much yet.
Okay. Second, this is more practical. In over HTTP, did you have to change the default header size in your servers? If not, how do you deal with the limitations of the header size?
Yeah, so our first version we did this, we encountered a handful of times where we actually broke services because we exceeded the header limits, and that causes mass propagation errors across everything. And so we really, going forward, want to be very strict of what is the data that is out there? How large can those payloads actually grow? We kind of set fixed limits of that data, so we kind of understand our total possible capacity, and then we kind of set limits and alerts around that to ensure that if we do grow beyond a certain point, we can throw errors earlier, only impact one service. Because probably once you get to going over header limits, it doesn't impact just your service, it impacts all the services in the ecosystem, and so you can quickly kill everything. So we really wanted to try to make those things fail faster by knowing what those limits are, enforcing them on a per service basis, per request basis.
Yeah, could you give us a high-level overview of like how would you inject a failure using context propagation?
So what we do is we have our edge router at the very top. I'll go back to this fun picture. So like the very top of this graph, we have our edge router that knows all the business rules around injection, knows how to read our actual database to figure out what those injections are. So we can set the errors on one system and then read those back. So our edge router is able to determine that and say, well, for service foo, I want to inject a failure when it calls service bar or whatever else. So that propagates through everything. And so as it gets down, once it reaches foo like, oh, there's a error on my context for my service. And if it calls bar, then knows, oh, I need to inject a failure, so immediately fails at that point. So we send that entire understanding through the entire request, so as it hits those services, it can easily detect that. Although going forward, we're actually looking at using service mesh to better enable that, so it can use a control plane instead of having this flow through. Because this thing has to get very large payloads. So again, coming back to the payload sizes and header sizes, we want to try to limit those sizes. Because if we start sending everything under the sun, how quickly our headers, our bandwidth, everything else grows exponentially. So we're trying to look at using control planes and service mesh to kind of offload some of that data. There's a question here. It's a very lively crowd. I like it.
Has any of this been open sourced?
Unfortunately, no. I don't think we have any kind of immediate plans. There's not really a lot of crazy logic in here. It's really just as long as you know how to build an interceptor. It's really just having an interceptor that knows how to pull those things out of the headers. The hardest part for us really is just that paved path. Like if you're trying to support every single client in the sun, it's almost impossible to scale out. But if you can really limit those implementations, it's much easier to manage. Then having some sort of process to manage data. Like early on, we had just empty or a basic key value pair store, and you could just put anything under the sun in there, and that was hard to manage. So by using our data models and having ownership defined, it's made it a lot simpler to understand all that data.
Yeah, I'm wondering if you could maybe help me understand like the request trailer side of things. Like I'm wondering, I hear we're putting like error information in those, but like I'm wondering how you decide what to put in the request trailers versus maybe just having on the like response itself. If there's an error that happens, like how do you determine what goes in the request trailers, what goes in the response? Like what does that breakdown look like?
So going up, or when we do bidirectional back upstream, the key has to explicitly say it's bidirectional. So if your key is not marked as bidirectional, so we're kind of going back to our models here, we actually in this case say bidirectional is false. And so in that case, if you make a modification to that data, it will only flow downstream. It will never flow back upstream. So we want to limit how much data we flow back upstream to manage that conflicts. So if we know that certain data needs to go back upstream for certain use cases, we'll set that to be true. And then if you make a change, so when your request comes in and then it hits that ultimate service implementation, that stub, if it makes a change to that data model, we automatically detect that. And then when the response goes back up, we know, oh, this context was changed. It needs to be updated and sent back to the client. So at that point, we'll add that as a response trailer going back up. Does that answer your question?
Yeah, maybe like so I get like that's a good explanation for like the functionally like how you determine like okay, this is like a field that I need to send downstream but maybe not back up. And that's like I guess like how the plumbing would work. But like how do you make the call of like maybe it's too generic for a question, but like what would be something that you would want to send back upstream versus not? Like is there like an examples or guidelines that you might have for that?
So our two biggest cases right now we're looking at is back pressure relief. So if we know that we're constantly getting overloaded and we want to kind of let the system know, hey, this service down here at the bottom is being constantly overloaded, we can kind of propagate that information back upstream to those callers. So, oh, future calls, I shouldn't call this instance. I should probably call a different instance to kind of offload that. The other big one for us was retries. Right now, we do a lot of times if we shed load or cause failures, we can quickly cause retry storms, which then causes DDoSes and impacts the entire ecosystem. Not good. So by using like retry budgets, we can put that number of retries into the context, flow it back upstream so that as calls in other places of the graph get used and be like, oh, we've already done 5 retries. I probably don't want to call anymore. Even though I've only done maybe 1 retry on my service, the whole thing's done 5, so I want to kind of start backing off on some of that calls.
Following on from that then, around the retries, how do you decide when you use the semantics of the protocol versus putting it in the metadata? Like just looking at the response code and making a decision and propagating another failed response up versus actually putting it into this context metadata. It seems like some of this might be duplicating things that the protocol already provides.
So we still let the implementation do or figure out how they want to retry. So we don't enforce what retries are or how they're done. We just, if whatever service, if it wants to fail on unavailable or fail on unimplemented or whatever else, like they make those decisions and it owns those decisions itself. The only thing we do within the framework for the context is if a retry did occur, we could send that information back upstream saying, hey, we did a retry at this point. But it's up to the underlying business logic to kind of determine what to do. Like our frameworks don't really care that happens at that point. It's just that we send that data back upstream or back downstream, and allow the frame or the libraries within the pave path frameworks to make those decisions of what should actually happen to it.
So basically, everyone gets the data, and then they get to
Yes.
decide what to do with it.
Yes. Are we good? Sweet. Well, thank you, everybody.